So, in the last, the 10th session, I told you about geotherms and melting curves and how interplay between the two, they sort of, by using them, you can find out how rocks melt. But these are more geometrical ways to do it. Now, in this session, I want to tell you how tectonics plays an important part in triggering melting of rocks. Let's start. So, tectonic processes of melting. Now, I must tell you beforehand that these are quite simplistic models, so that you can sort of try and understand it. It's not the only way or not the only thing that can be done. There can be many complicated, intricate ways in which things can happen. But for us to understand how this pressure temperature changes do occur. That's what is important. So, in the last one we also discussed that melting is possible if the geotherm position can be changed, especially to higher temperatures. Then you can mutually intersect the melting curve and the geotherm. Or what you can do is you can shift the melting curve to lower temperature so that the melting curve intersects the geotherm, or you can have both operating together. Now, I will try to put out some ways in which this can be done. So, this is temperature and this is pressure. So we have the geotherm and we have the melting curve. So, melting curve and geotherm. So ordinarily, you will not get melting according to this situation. Now let me draw a figure on the right hand side, and then we can see how things can be triggered. Let's say this is a crustal section that I'm drawing, a crustal section. Here is the surface of the earth, and here you have the mohawk, and here you have the mantle rocks. This thickness, as we know, in continental areas are roughly 35 kilometers. In the oceanic areas, this thickening, this width of the crust is much thicker, to 5 to 8 kilometers on an average. That's what is the thickness of the oceanic crust. Now, within the crust, as you can understand, that these are the isotherms. So we have T1, T2, T3, T4, and so on, where T4 is greater than T3, is greater than temperature T2, and greater than temperature T1. So as we go down the Earth's surface, the temperature increases. Right? Let's imagine this. Let's imagine. Due to some processes, due to some tectonic processes, normally some sort of extensional processes, like in mid-oceanic ridges or divergent margins. Let's say because of this extension, what happens? So if you extend the crust, then the stretching is in this direction. And so if you have a crust like that, and if this experiences stretching, then what happens is you generate this type of a situation. So this is the mantle. So what you have is here, you produce the mantle, you bring the mantle up, and so what happens, there is some amount of melting in the mantle. So sometimes melts are generated way below the mantle, and these melts move up to the Earth's surface, and this melt sort of ponds itself below the Earth's crust. This melt has a density so that it cannot cross the crust, but it forms a cone-like material on the crust. So when this melt cools down, it releases heat. So when it releases heat, what happens is your T4 goes to T5, your T3 goes to T4, your T2 goes to T3, and your T1 goes to T2, and similarly this one goes to T1. So what is happening when you have a melt ponding from below the mantle onto the crust? What's happening is that the isotherms that were there in the crust, they change positions. So what happens? The lowermost part, which was at T4, changes to T5, T3 changes to T4, T2 changes to T3. So what is happening? The crust is getting heated. But there is, let us make a simplified assumption, the depths of this, at this point, let's say, the depths are remaining the same. So if you look at the geotherm, say this was, say as you go to the geotherm, it was initially T4, T3, T2, T1, and this one was 0. So what has happened now, because of the emplacement of this hot material at the base of the crust at the maw, what happens? T4 has now become T5, and T5 has become T4, and T2 has become T3, and T1 has become T2. So what is happening actually, this geotherm which was in this position, this geotherm shifts to another position. Have you understood? A new position where each point of the geotherm, you see, at this point there is no change in pressure, but T1 changes to T2. At no pressure change, T2 changes to T3. So what is happening in this direction? The pressure remains the same, but the temperature increases. So essentially what we are looking at isobaric heating. Isobaric means the pressure at a particular level is not changing, but the temperature is increasing. So what will happen to the geotherm? Each point on the geotherm will experience an increased heat. Obviously, the temperature at the bottom the increase should be fairly high. So after a particular time t, you remember, it was the geotherm was dP by dt at a particular t. Now if you change it to another t, it will have a different geotherm. And now look at this position, this cutoff position. Before the geotherm was like this, but after that the geotherm became like this. So at this, up to this pressure, there will be no melting. There will be no melting. But below this pressure, because the geotherm intersects the melting curve, you will trigger melting below a particular depth. Now this is what is called isobaric heating. Isobaric heating. That means pressure same, but the temperature increases. Why was it? Because there was some amount of magma that reached the base of the crust by some process and bonded below the monophasic discontinuity. And when this magma cools, it heats up what is above. Because below it doesn't heat up because it's hotter. So, but here it heats, it transmits the heat conductively through the crust of the earth. And the different geotherm then snaps up So snapping of these temperatures isotherm upwards causes the geotherm to change its geometry. And this causes intersection of the melting curve with the new geotherm. With the old geotherm, there was no melting. But with the new geotherm, there will be melting. So remember one thing, so that is important. Isobaric heating triggers melting because this shifts the geotherm isobarically or at the same pressure to high temperature. So that's one mechanism by which you can trigger melting. Let's look at some other mechanisms. Let's say there is a crust and you can understand the isotherms. I'm drawing a few lines just for reference. Okay, so this is T3, T2 and this is T1. So this is the crustal section, this is top. This is top, a crustal section. And let's say we draw a line like this. A line like this. So what we have on this line, this line actually is the trace of a fault plane. We have talked about fault planes. So let's say this is a fault plane. So what happens, now let's see what happens. If this is a normal fault, then this would be the direction. Remember, the hanging wall on this side moves down relative to the foot wall. Remember, this is the foot wall and this is the hanging wall hanging above the foot wall. So if it's a normal fault, it would trigger this part to slide down the fault plane. Have you understood? Now, if this is so, then let's do the following thing. Let's draw a circle. Have you understood? A circle. So what will happen now if the faulting actually takes place? Then what will happen? Say this one at that time was T3, T2, T2, T1, and this was the surface, remember? Now, this point, which was between T1 and T2, this point between T1 and T2, I will draw now a sphere. This point was here. And here, the point is T1, T2 and T3. So between T1 and T2, the other point is here. Have you understood? These two halves were essentially here, between T1 and T2, and the fault plane through it. Now what has happened? This half has remained here, and this half has remained there, has gone down there. So there has been a displacement because the faulting, this is a normal fault. Now let's see what happens. You see what is happening. I draw this line, and here you see this distance above this is H, rho and G. This causes the pressure. Now, if you look at this is now H, rho, G. Yes? Now you see here something interesting. There was an overload pressure H, rho, G before the movement. After the movement, there is no drop above it, you have air or water or something very light. So what happened? There has been a very fast loss in pressure. But temperature-wise, it remains the same. This happens in the footwall. I will repeat. In the footwall, what has happened? This h rho g distance from the surface to this point, it's marked here, but you can see that here there is no rock because that rock has slid down. So what happens is a rock column of h rho g is lost. That means the pressure above this point has decreased, although the temperature has not changed significantly. Right? No. If you look here, it is not the case, because here h rho g, that broken line here is still here, h rho g. So that height did not change. That height in the hanging wall has not changed. That height still remains. And the temperature is between T1 and T2. But this is in the hanging wall. But if you look at the foot wall, there has been a major change. The foot wall has lost pressure. So how will this reflect in the melting curve? Now you can see. So this is temperature again, temperature, and this is pressure. So once more, it's the geotherm, and this is the melting curve. This is the melting curve, and this is the geotherm. Now if you see this point here, let's say this point here is here. So what has happened? In the footwall, this point has gone here. And therefore another point also went up. And another point went up here. But just look at this. So what has happened is the geothermal position is here. Do you understand? All of these points of the old geotherm has moved up relative to the old geotherm. This is h rho g that we were talking. So what has happened? The temperature has remained constant, but the pressure has changed, has decreased. This is the loss in pressure. So this is what is called isothermal decompression. This is called isothermal decompression. That means loss of pressure or loss of overburden at the same temperature. So what has happened here? Last time we talked about isobaric heating that might change the geotherm and intersect it with the melting point. Here, the tectonics that I've shown you is completely different. There is no new magma, nothing. Just a normal fault, and the hanging wall responds in a foot wall responds in a different way than the hanging wall. This refers to the foot wall. So the foot wall here has lost pressure. Here also you see the foot wall pressure loss has been less. Have you understood? So that way, last time when I wrote, I did this arrow. This was isobaric heating in the first case, which I erased off now. Here is the case now where you have isothermal decompression. Isothermal decompression. So these are some of the tectonic processes that cause a geotherm to intersect the melting curve. The geotherm to intersect the melting curve. Now, having said this, let us draw some geometric ways to deal with these tectonic processes. I will not go into the greater details. It's not necessary at this stage. So we have temperature, we have pressure, and this is the melting curve, and we have a geothermal. And if we have a point here, then we can intersect the melting curve by going this way. Right? This is what we did. Isothermal decompression. Then we had isobaric heating. We can also have a situation like this, where it is heating and loop. So here P increasing, P increasing. Heating and loading means pressure increasing, temperature increasing. Isothermal decompression is pressure decreasing. Isobaric heating means temperature increasing. When I don't write the other one, it means that's constant. So, this is the different tectonic ways by which it's shown geometrically here, but I gave you the background, what should I say, the background tectonics, at least in two cases, I gave you that such situations can arise and trigger melting. Essentially, if I draw a diagram into half, you can see that if you go this way, if you go this way, if you go this way means decreasing pressure and decreasing temperature. You will not have melting. If you go for cooling, you will not have melting. If you go for, you see, loading and cooling, you will not have decompression. So all processes that happens to the high temperature side of this line, these are possible. So essentially, I have shown you decompression, isothermal decompression and isobaric heating. Say for example, I could tell you that okay, we have plus heating. That's also possible. Decompression and heating. Which part am I saying? Decreasing pressure and increase of temperature. So the part that I am trying to show is this part. You see, this is the part that I am trying to show. Decompression, decreasing pressure, and increasing temperature. Now you can ask me what could be the tectonic process. I'm not going to tell you because it becomes complicated and it becomes very boring and it becomes very big, and then we sort of move away from the topic. We have to finish this huge course in a very small time. And so I tell you, please excuse me, if I go on doing this, I will take about 1 week class to tell you more about this. In advanced classes, you take at least 3 weeks to finish this. So I'm trying to sort of abridge it and give you an insight that this change in the position of the geotherm is not normal. It happens because of certain earth processes that trigger changes in the geotherm and as well as changes in the position of the melting curve, decreasing temperature of the melting curve, and this can trigger melting in the rocks. Now, you please write down, I will give you a problem, and you think about it, you read about it, and please write down. Which amongst these processes, or for example, let me state it that way. I have shown you photographs of divergent margins, I have shown you photographs of conversion margins. In both, you generate melting. In both, you generate melting. I've shown it in 7 slides, I think slide 5, or I don't remember which one. But you have divergent margins as well as convergent margins. In both, you trigger melting. Right? You trigger melting. In divergent margins, you melt the mantle and the melt comes up to add to the crust. While in a convergent margin, the oceanic crust that you produce subducts below the continental crust, melts. So the oceanic crust that you produce in the divergent margins is destroyed in the subduction zone. Now, what I'm asking you, the process of melting in the divergent zones and the process of melting in convergent zones are different. They belong to something like this, but I want you to read it and find out what is the main difference in the process of melting in a divergent margin and in a convergent margin. What are the essential differences in processes? There should be something here. I'm not going to detail about it, but you have to tell me that. Whenever I ask, you have to tell me, how is it possible? What are the different processes that operate due to melting, that induce melting in divergent margins and induce melting in convergent margins? What are the different processes? Right? Fine. So now we see that we can trigger melting in rocks because of certain tectonic processes that operate. Next, we will go into a field from which we will start to learn about how rocks melt, how rock crystallize, and we will include a little bit of thermodynamics to understand it. Many of the reactions you already know, but we could just about try and give you some little introduction before we go into the main topic, so that we will talk about a little bit about phase diagrams. Very simple phase diagrams, but that will give us great amount of insights into how melting occurs in rock, how crystallization occurs in melt. These are two end-member processes. How do they operate? What happens? What is the dynamics of the system? This is what we will learn. So we will restrict ourselves to understanding binary phase diagrams. Binary phase diagrams. This is what we will concentrate. Now, we will try and understand crystallization and melt. How does it happen? Remember, a rock comprises of minerals. So, when you crystallize a magma to produce the minerals. And when you melt the minerals to produce the magma. How is it done? But before that, I will make a little bit of introduction to you. You must have heard or read, I'm sure, of an equation which says G is equal to G0 plus RT ln activity. I'm sure you know it. But I think I should clarify a little bit. First, the simple ones. R is the universal gas constant. Normally nowadays joules is taken as the unit for heat, etc. So R is in joules per Kelvin per mole. R is in joules per Kelvin per mole. Temperature T is in kelvins. This term is called activity. I think you know this term. Activity. Now, activity is difficult to define like this, but you must have read it as the active mass of a substance that takes part in a chemical reaction. That is the definition that is given to you. Activity is the active mass of a substance, that participates in a reaction. We will leave it at that. You must be knowing that normally there are several things. I think before this I shall introduce you to system. One is called the system, a thermodynamic system. What is a system? System is a part of the universe which you can choose at will. Say for example, you can say your body is the system, then everything else around it is a surrounding. You can say in a rock that rock is a system and everything around it is a surrounding. You can also say that within that rock, a particular mineral is my system and everything around it is a surrounding. So the choice of a system depends on you. But the moment you choose a particular space in the universe as your system, the rest does not have any distinguishing characteristics except for the surrounding. There is no more divisions in that. It's a monolithic thing. It's a thing that is very uniform. Even if there is heterogeneities, you can't take it into calculations. So you have a system and a surrounding. And you have what is called a system-surrounding interface. There are three types of system, as you know. One is called isolated system. Isolated system is where the system does not exchange mass or energy with the surroundings. That's an isolated system. This is a very idealized system. It doesn't work that way. Then we have a closed system. Now this is commonly used. In a closed system, the system exchanges energy but not matter with the surrounding. So in a closed system, the system exchanges energy with the surrounding. It's an equilibrium with the surrounding, but there is no mass transfer across the interface. And in an open system, the system and the surrounding exchange both mass and matter, and both mass and energy across the system. So the mass of the system is changing continuously. But in a closed system, the mass remains the same. So these are the three types of systems. That is thermodynamics. In geology, normally a system consists of an aggregate of minerals. An aggregate of minerals. There can be one type of mineral or many types of minerals together, tightly bonded by certain characteristics. They form rocks. So in our geological situation, we have system comprises a monomineralic aggregate or multimineralic aggregates. Now these multimineralic aggregates or mineral aggregates that we are saying, these minerals have certain definitive properties, definitive physical properties, like their density, their refractive index, optical properties, physical properties. They have certain characteristic properties by which it can be separated from another mineral. Also, they have different compositions. Although, you know polymorphic transformations. So polymorphic transformations, say for example ice and water and water vapor, they have the same composition but they have different physical properties. So physical properties is the most important part. So ice, all these, say for example, say graphite and diamond, you have all read about it, they are polymorphs of carbon. They have the same composition, but the properties of graphite and the properties of diamond are very different. We don't have the lab class, otherwise you could have seen more. So what happens, all these mineral phases, different mineral phases, that forms a geologic system. Essentially, each of these minerals are called phases. Each of these minerals are called phases. They have definitive physical characteristics. Their compositions may be very different from the other phases, and they have defined boundaries by which you can separate one phase from the other. Say graphite and diamond, if both of them are there, it is not possible to have a diffuse boundary because their physical properties are different. You can't have any diffuse boundary between graphite and diamond. So they have definitive boundaries. Now, the phase, the composition of a phase may be unique. Like, say for example, we were talking of graphite and diamond. Graphite contains carbon, carbon and only carbon. Diamond contains carbon, carbon and only carbon. But say for example, quartz. It's a mineral. It's a very common mineral. Quartz. The formula is SiO2. Silicon dioxide. It's a crystalline form of silicon dioxide. Have you understood? But it is essentially composed of SiO2, not necessarily elemental silica and elemental oxygen. No. Silicon dioxide. Graphite and diamond have elemental carbon. Say there is another mineral, let me write a simple mineral. Say there is a mineral called olivine. There's a mineral that makes up a large part of the mantle. Now the formula for olivine is Mg, Fe whole twice SiO4. This is the formula of Mg2 olivine. Mg, Fe whole twice SiO4. Remember, I was talking to you in the earlier lecture, we were talking to you about SiO4 tetrahedra with 4 negative charges. These are balanced by Mg2 plus and Fe2 plus. 2 of them makes 4 positive charges and this balances this reaction. So olivine is a mineral, but whose compositions vary. But whose composition is given by this formula, Mg, whole twice SiO4. I can split it into Mg2 SiO4 and Fe2 SiO4. It's not a mechanical mixture, it is a chemical compound of Mg2 SiO4 and Fe2 SiO4. It's not a mechanical mixture, it's a chemical compound. It's called a solid solution. So you have Mg2 SiO4 as one component of olivine and Fe2 SiO4 as another component of olivine, and these together can be mixed in any proportion so that you will get MgFe whole twice SiO4. So in this olivine, XMg will be equal to Mg divided by Mg plus Fe. And of course, XFe will be equal to 1 minus XMg. So we can define the composition of the olivine in terms of 2 end members. That means these 2 end members are not mechanical mixtures. These are not salt and sugar, but they are chemical compound or a solid solution between these 2 end members. So this is called, these then are called phase components. These Mg2SiO4 and Fe2SiO4, these are called phase components, or the number of components that make up the phases. Not a mechanical mixture, but a chemical compound or a solid solution. So you have system, phases, and phase components. Phase components. Have you understood? In quartz SiO2, this quartz is a mineral and the component is one. In olivine, the mineral is one, but the components are two. There can be much more complex relationship. We don't go into that. We make these easier for us to understand. We do not bug up, we understand. After this, we have one last thing before we move on. One is called system component. System component. Now, you write down the definition. What is a system component? It is the minimum number of components, chemical components, that describe the composition of the system. That describe the composition of our system, which is a geological system. So, what is the system component? It is the minimum number, underline minimum, the minimum number of chemical components that describe the chemical variability of a system. Just let's talk about it. Say, for example, if I have quartz, it has a formula of SiO2. That means I can write SiO2 as equal to Si plus 2O. Or I can write SiO2 is equal to 1 into SiO2. Why am I writing like this? Here, I can describe SiO2 by this. Two components. And I can write SiO2 as SiO2. Which one will I choose? Remember the definition. Minimum number of components. So, what is the number of components here? SiO2. Because you can describe the chemical variability of your quartz with just SiO2. You don't need Si plus 2O, that will make it two components. Let's go to another example. Let's say there is a mineral Al2SiO5. Since I'm writing it, say for example there are three minerals, sillimanite, kyanite, and andalusite, having the same composition. That means sillimanite, kyanite, and andalusite are three polymorphs having the composition Al2SiO5. But they are very distinctive properties. They are different as far as phases are concerned, but their composition is the same. Right? Just like graphite and diamond. Their properties are different, physical properties. Chemical composition is the same. Same. Now, I can write Al2SiO5 as 1 into Al2SiO5. I can write Al2SiO5 as Al2O3 plus SiO2. I can also write Al2SiO5 by Al plus Si plus 2.5O2. I can write this. Here it is a 3 component. Here it's 2 component. Here it's 1 component. So what is the system component of Al2SiO5? 1 Al2SiO5. Not 2 Al2O3 and SiO2. No, minimum number. And not Al, Si and O. No, because it's frequent topology. So this is a little brief introduction into a little bit of thermodynamics before we go into the find this equation. Now, we go to this equation quickly. We will go into the details later on. We know, coming back, we know that this A is equal to activity. Acha, what is the unit of this term? R, I told you, is joules per Kelvin per mole. So multiplied by temperature, then this term is joules per mole or whatever it is. Because activity is a dimensionless quantity, doesn't have any unit. So if this is joules, then this is also joules, and this is also joules. These two terms are called Gibbs free energy terms. Gibbs free energy. Free energy terms. Their unit is joules. But what is the difference between these two free energy? Now for this, let us do one. You know, the activity of a pure phase, the activity of a pure phase is 1. Have you understood? Activity of a pure phase is 1. So if I take a pure phase, activity is equal to 1. If this is 1, then this term vanishes. That means what? G becomes equal to G0. Yes or no? So what is G now? G is equal to G0 now if activity is equal to 1 for a pure phase. That means this is the free energy of a pure phase. G0 is the free energy of a pure phase. And what is G? G is the free energy of the phase. Have you understood? Or tomorrow we will see it's not the phase, it's called a phase component. G is the free energy of a phase. It has two parts. One is this part, the free energy contribution of the pure phase. And this one, what is it? This is the free energy component of impurity. If activity is less than 1, that means the phase is not pure. That means this term is negative. That means G is less than G0 for impure phase. But G is equal to G0 for pure phase. So, G0 is the free energy of the pure phase. G is the free energy of the phase. It contains two parts. The free energy due to purity, and this is the free energy of impurity. So if it is impure, then G will be smaller than G0. If it is pure, G will be equal to G0. We will continue in the next class. Thank you.